Hey class, let's take a quick look at periodic trends. What are they, and not only what are they, but how can we explain and justify them? First of all, I took this outside and there is a loud truck humming somewhere nearby. Hopefully it's not too distracting. But what should we have learned thus far in our unit? You should know that elements in the same column have the same number of valence electrons. And because of that, they have similar electron configurations, and because of that, they have similar physical and chemical properties. And we're going to take a look at that in the development of the periodic table. This is a very brief recap of the periodic table development, and there were more people involved than this, but let's boil it down to Mendeleev and Meyer. They both organized the elements by weight and chemical properties. They didn't know about the atomic number. Mendeleev got credit because he was first to publish his stuff. Mendeleev left blank spaces in his table because he insisted that there were elements with similar characteristics that needed to go there. He just didn't know what they were. And later on, he identified quite a few, including germanium and gallium. Now, Moseley discovered the atomic number. And when he organized the elements based on atomic number instead of what Mendeleev did, turns out that they fell better into the correct locations. Moseley's organization still left holes in the periodic table, and that did eventually lead to the discovery of new elements. On a side note, that truck humming in the background, turns out they're spraying trees behind me. Just in case you're ever on a show and you need to know what that sound is. Well, how can we explain what's happening in an atom and which elements are likely to give away electrons, which ones want to steal? Well, we always talk about the electrons, right? We always talk about how many they have, the electron configuration, what orbitals they're in, and all that stuff. But what we really need to think about is Coulomb's law. And remember, Coulomb's law simply says opposites attract, like charges repel, and the distance between them affects it. So over and over and over again, when you explain the trends in the periodic table, you need to go back and think about how strong is the positive-negative attraction between the nucleus and the electrons. And then you need to think about, well, how far apart are they? Those are really, really important factors here. The force increases when the nuclear charge increases. If you have a stronger nucleus, there's going to be a stronger attraction. Just think of it being like a stronger magnet. The force is going to lessen as the electrons get farther away. I mean, that makes sense. I mean, if you hold a magnet 6 feet away from a metal refrigerator, is it going to attach to the refrigerator? Of course not. Right up next to the refrigerator? Yeah, it's going to stick. The more electrons there are, the more electrons repel, and then they tend to spread out. That makes them bigger. The repulsion of electrons can actually cancel out the effect of the nucleus's attraction. So even though the nucleus is attracting the electrons, those electrons spread out more, it's going to kind of balance out in the end. There is something called the effective nuclear charge, and this is important, and we'll walk our way through this with one of our assignments. But the effective nuclear charge is the net attraction between the nucleus and those outer electrons. And this can be decreased by electron repulsion. It can be decreased by shielding of the inner electrons. Lots of things going on. But what we're looking at here is the overall net effect of positive-negative attraction. The effective nuclear charge is always less than the actual nuclear charge. There's always something lessening the effect of the nucleus. Apparently they're done spraying, so it's much, much, much more quiet outside. And now I can hear the birds again. It's so wonderful. When we talk about how strong is the nucleus, one of the things we need to talk about is screening or the shielding effect. Well, when you think about all the electrons, you have all of these orbitals moving away from the nucleus. The outer electrons are the ones farthest from the nucleus. All of the other electrons are what we call core electrons. Those core electrons are a little bit closer to the nucleus, and they shield the nucleus. They actually decreased how positive the nucleus seems. I'll give you an example, and this is from a textbook. the textbook says, put a light bulb in a lamp, no lampshade, turn the light on. It's bright, right? Now put the lampshade on. What happened to how bright the light seemed to be? It's decreased because the lampshade shields some of that light away from you. I like to use this example as well. Let's say we have a student in the classroom and there is somebody looking for this student. Psychotic, crazy. We don't want this person to find the student. Well, if we all stand around this student sitting down, we're standing around and we're acting like we're looking at a microscope or something. When this individual steps into the room and looks, they won't see that student because we're shielding that student from that person. So the takeaway is inner electrons shield the nucleus. So the inner electrons reduce how positive that nucleus seems to be, and that ultimately decreases the attraction between the nucleus and the outer electrons. Let's just talk a little bit more about the effective nuclear charge. You need to consider where the valence electrons are, how far away they are, what orbitals they're in, etc. Note that the s orbitals are the closest ones to the nucleus than any other orbitals, and that's because the s orbitals are spherical. Remember all those weird shapes, the double like dumbbells and the double pacifier and the four-leaf clover things? All those different shapes put the electrons farther from the nucleus. So the s orbitals are closer, and that can affect the attraction. There are two general rules you need to know. One for going across a period or a row, and one for going down a column. So let's look at the row first. As you go across a row, the effective nuclear charge increases. Now let's think about why. As you move from lithium to beryllium to boron to carbon, well, what's changing? You're gaining another proton in the nucleus. So every time you move over a column, that nucleus is becoming positive by 1. Yeah, you're also adding electrons, but they're all basically the same distance away. We're not changing necessarily too much how far away they are. So as you go across a row, the number of protons increases, and this will increase the effective nuclear charge. And this is why you notice in fluorine doesn't like to give up its electrons. The nucleus is so strong, it holds all those electrons in place and just pulls in another one very, very easily. As you go down a column, the effective nuclear charge is going to be less because, well, the electrons are just farther and farther away from the nucleus. And part of that goes to those orbitals and how diffuse those electrons are, the cloud density, where do we actually find them? And all of that plays into it. But the big takeaway is going across a row, the nuclear charge increases, but going down, it decreases. I just want to take a quick moment and talk about a couple of different atomic radii definitions. The non-bonding atomic radius, also known as the van der Waals radius, it takes the shortest distance between separating two nuclei during a collision, divided by 2, and you get a radius. A bonding atomic radius is you find the distance between two bonded atoms, divided by 2 to get the bonding radius. And this is smaller than the non-binding radius. So when we are talking about atomic radius, we are talking about the bonding atomic radius. If it makes it a little bit easier for you, just go back to geometry. Think about a circle. What's the radius? It's from the center out. It's not exactly the same when we're talking about the atomic radius, but if that helps you get a visual for a radius, go with it. How do you calculate the bond length? Well, there's resources like in our book, and you simply find the atomic radius for one element, find it for the other one, and you add them up. So if you're looking at C and Cl in CCl4, you look up the two values and you add them up and you get the answer. It's pretty easy. There are 4 periodic trends we're going to discuss: atomic radius, ionic radius, ionization energy, and electron affinity. So let's start with atomic radius. As you go across a period, the atomic radius decreases. There are a few exceptions, which we'll deal with later. Why does this happen? Well, remember, as you go across a row, the effective nuclear charge increases because there's more protons. This pulls the electrons in more tightly. It makes the radius smaller. We'll get into some of the exceptions later, but I'll give you one quick one. When you go from nitrogen to oxygen, oxygen is actually a little bit bigger than nitrogen, and it has to do with where we're placing the electrons in the orbitals, but we'll talk about that later. As you go down a group, the radius becomes bigger. And that makes sense because you're adding electrons, you're having more and more and more orbitals, they're farther and farther from the nucleus, the positive negative attraction decreases, it gets bigger. Second periodic trend, ionic radius. Well, let's just start with what is an ion. Remember, an ion is something that has gained or lost electrons. The size depends upon a few things: the nuclear charge, number of electrons, the orbitals involved, and just exactly where we find the electrons. Cations, remember cats are positive because cats have paws. I know, stupid, silly. But when an electron is lost, the electron-electron repulsion is actually going to decrease. So think about it. If you have all these electrons and you remove one, the electron repulsion decreases and they actually get closer to the nucleus. It's kind of like if you're standing in a circle with friends and somebody leaves, doesn't everybody kind of take a step toward each other and get a little bit smaller? Anions are when you've added an electron. Again, this is going to increase the electron-electron repulsion. This is going to force them to spread out, and the radius is going to go up. So cations lose electrons, they become smaller. I mean, it kind of makes sense. If you lose your arm, you're going to get smaller. Anions are adding electrons, causing more repulsion, more expansion. They get bigger. So as you go down a group, the ionic radius is going to increase for the same reasons as the atomic radius. And as you go across a row, not quite so clear. It's kind of all over the place. And that's because as you go across a row, some of those are cations, some of those are anions. So we get this kind of fluctuating pattern going on that can be explained if you just stop and think about it. One of the easiest ways to look at that relationship with the ionic radius going across a row is to create what is called an isoelectronic series. And this is where you put elements in a series according to how they are on the periodic table, but they all have to have the same number of electrons. So look at the example I gave you. O -2, F -1, sodium +1, magnesium +2, aluminum +3. First of all, don't they all have 10 electrons? Oxygen normally has 8, and you're adding 2, you get 10. Fluorine has 9, you add 1, you get 10. Sodium has 11, you take away 1, you get 10. Magnesium has 12, take away 2, so on and so forth. And then those are the ionic radii. So once you line them up in an isoelectronic series, take a look at the trend. What happens as you go through this series? The ionic radius decreases. Now this should make sense to you. Oxygen gains 2 electrons. Electrons repel, they push away from each other. It should be the biggest. Go all the way over to aluminum now. Aluminum has lost 3 electrons. So as those 3 electrons got lost, those electrons got closer and closer to the nucleus, which makes it smaller. Trend number 3, ionization energy. I like to abbreviate it with an I and an E because I'm lazy. The definition for ionization energy is the minimum energy required to remove an electron from the ground state of an isolated gaseous atom or ion. Values are always positive because energy is always absorbed. They need energy in order to remove the electron. You're going to see the terms first ionization, second ionization energy. It's just referring to the first electron removed or the second one removed or the third one removed and so on. The greater the ionization energy, the greater difficulty it is to remove an electron. So if it says it takes 10,000 kilojoules per mole versus 2,000, it means that 10,000, it takes a lot more energy to remove that electron. I like to kind of relate this to taking away a lollipop. If I go over to a teenager and say, give me the sucker, most of the time they just hand it over. Have you tried taking a lollipop from a 2-year-old? Mine, mine, mine! And they just hold on and cling to it, and you act like an idiot trying to get it away from them. So the more energy it takes, the harder it is to remove. As you remove an electron, remember what happens. There's less repulsion. The electrons get closer to the nucleus, and it gets more difficult to remove an electron. So if you look at this data table, you'll notice as you go through successive ionization energies, it gets more and more difficult. Like look at Si, for example. The first electron requires 787 kilojoules per mole, and then almost 1,600, 3,200, about 4,400. So every time you remove an electron, it becomes a little bit more difficult to remove the next electron. Now, what I do really want you to notice is that once you have removed the valence electrons, there is a tremendous jump in energy. So look at aluminum. Aluminum has 3 valence electrons. Once you remove that third, you go from, and I'm rounding here, 2,800 to almost 12,000. So how can you figure out how many valence electrons something has? You look for that giant jump in energy, and you count how many were before the giant jump. Now you know how many valence electrons you have. And based on that, you can figure out all sorts of things like, okay, if I have that and I pair it with sodium, what would be the chemical formula? It's kind of cool. Let's keep going with ionization energy. As you move across a period, the ionization energy increases. In other words, it's going to take more energy to remove an electron as you go across a period. Remember that your effective nuclear charge increases, the radius is getting smaller. As you go down a column, everything decreases. The atomic radius becomes bigger, the positive-negative attraction decreases. It's easier to remove an electron. It requires less energy. The S and the P block elements show a large range of values than do the transition elements. The transition elements tend to increase ever so slightly, not a whole lot of variation in the F block. And the variations are pretty easy to explain. As you go from beryllium to boron, the reason why there's such a difference is because boron's last electron is placed into the p orbital. Well, that's quite a bit farther from the nucleus, so it's easier to remove. Because remember, as you go across, you would expect the ionization energy to continue to increase. But when you go from B to BE to B, it actually goes down? Well, yeah, because that electron's farther away, it's easier to remove. I mentioned this one before. As you go from nitrogen to oxygen, nitrogen has total of 5 valence electrons. 2 are in the S, and then there's 3 that go into the p orbitals, and we put 1 in each of the p orbitals. They're in their own orbital. Well, when you go to oxygen, you now need to put 4 in the p orbital. You have to double up. And when you put 2 into one of those orbitals, it makes them spread out, it makes them farther from the nucleus, and it's actually easier to remove an electron from oxygen than nitrogen. If you just think about what's going on with all of these things, it's pretty easy to explain the patterns we see. While we're talking about ions, let's do a side note on writing an electron configuration for an ion. Please be careful on quizzes and tests. Sometimes I ask for the electron configuration of an ion. So ask yourself, what does that element do? Does it gain or lose electrons? And then adjust from there. So start, like for oxygen, start with oxygen's electron configuration. Note that it's going to gain 2 electrons and change the P4 to P6. Electrons are always removed from the orbital with the largest principal quantum number. So if you look at my example for lithium, 1s2, 2s1, you remove the 2s1 first. The transition elements are kind of weird because you have, 4s and 3s and all sorts of weird principal numbers. Go with the largest principal number, which in the example given is 4, and those are the electrons that go first. So you remove the 4s2s first, then you start removing from the ds. And what if you have s and p orbitals with the same n value, like as in krypton, 5s2, 4d10, 5p2? you're going to remove the P's and then the S's before the D's. Just to let you know that. And when adding electrons, you always add to the empty or partially filled orbitals first. Let's talk about the fourth and final periodic trend, electron affinity. On the next slide, I'm going to compare electron affinity to electronegativity, and I am ashamed to say that I used to use these words interchangeably, and I shouldn't have, so I apologize. We'll do that in a minute. First of all, the electron affinity is the energy change that occurs when electrons are added to the lowest energy unoccupied orbital of a free atom. These are typically negative values as energy is released. If the value is positive, it means the electron is not going to attach. Halogens have the most negative electron affinities. When they gain an electron, they become stable with a noble gas configuration. Anytime an added electron resides in a higher energy sublevel, the electron affinity is greater than 0. Think about Be or Mg. If you add an electron, that goes into an empty p orbital because Be and Mg, they have a filled s orbital. Examine the nitrogen column. They have 3 half-filled p orbitals. If you add an electron, the repulsion is going to increase. So this column either has positive values or values less than the elements to the left. When you're going down a group, there's not a whole lot of change. As the radius increases, nuclear attraction decreases, but the valence electrons are more spread out and there's reduced repulsion. So the reduction in attraction is counterbalanced by that reduction in repulsion. So let's go ahead and talk about electron affinity versus electronegativity. And I got to be honest with you, I really honestly thought they were the same words, same meaning. Turns out they're not. So I went ahead and did a little bit of a dive on this just to clarify it for you because I want you to know more than I did. And you can see that I did cite my source for this. Well, the electronegativity is the ability of atoms to attract electrons from other elements, while electron affinity relates to the energy released when it acquires an electron. The electronegativity applies to a single atom, where electron affinity can apply to an atom or a molecule. Electronegativity is measured in Paulings. Electron affinity is measured in either kilojoules per mole or EV voltage, basically. Electronegativity is actually a qualitative piece of data, while electron affinity is quantitative. The factors that affect electronegativity is the distance between valence electrons, the atomic number, the charge of the nucleus. Factors that can affect electron affinity, again, atomic size, nuclear charge, electron configuration. For electronegativity, fluorine is the most electronegative. Francium is the least. Polar opposites on the periodic table. Now, what's weird, though, is for electron affinity, chlorine has the highest electron affinity, with neon being the lowest. I just wanted to clarify that. They're not the same words, and when we look at the periodic trends, we really should be talking about the electron affinity rather than electronegativity, although some textbooks do talk about electronegativity. We could talk about either trend. They're basically kind of the same trend, but they're not the same vocabulary word. Now that we've talked about the trends, let's talk about one other thing on the periodic table, and that is the type of elements that you find. First, let's discuss the metals. Sometimes you're going to hear how much metallic character does an element have. Well, the more that element seems like it's a metal, the more metallic character it has. Metallic character increases as we go down a group, and it decreases as we go across a period. And that should make sense to you. Think about the periodic table. Majority of the periodic table are metals, but as you go across a row, don't they turn into metalloids and nonmetals? Exactly. The properties of metals include a shiny luster. They're malleable, meaning they could be bent or shaped. Ductile, they could be drawn into a wire. They're conductors of heat and electricity. Most metal oxides are ionic solids that are basic. They tend to form cations in solution. Most are solids, obviously not mercury. Most have high melting points, and most have low ionization energies, meaning they love to lose electrons during reactions. Transition metals can form more than one cation. You've already memorized these. Metals tend to bond with nonmetals to form ionic bonds. Next type of element, nonmetals. So these are on the right-hand side of the periodic table. They don't have luster. The solids are brittle. Some are hard, some are soft. They're poor conductors of heat and electricity. Pretty much everything that a metal is a nonmetal is not. Non-metal oxides are molecular substances that form acidic solutions. They tend to form anions or oxyanions in aqueous solutions. They can be solids, liquids, or gases. They have lower melting points than metals. They have strong electron affinity, so they gain electrons when reacting with metals. They typically gain enough to fill their p orbitals to act like a noble gas. Compounds made of just nonmetals are molecular and are low melting solids. There are 7 nonmetals that are diatomic: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Bromine is a liquid, iodine is a solid. You need to memorize these for when you're writing equations and whatnot, writing formulas. Some people have come up with sayings like, have no fear of ice cold berries. I did have a student one year who made up her own, and she said, have no fear of ice cold beer. Don't want to advocate alcohol, but if it works for you, go with it. Just memorize these. I just remember because hydrogen is by itself, and then NOFClBri kind of make a little number 7 on the periodic table. And lastly, we have the metalloids. These are the ones along the stair step. And just note, not every resource agrees on how many there are. Some will say there are 6, some will say there are 7, and some will say there are 8. Just go with whatever resource your book is. Metalloids are both kind of like metals and nonmetals. They look like metals, but they tend to be brittle or not malleable. They either do not conduct heat and electricity, or they kind of conduct heat and electricity. Some are what we call semiconductors, and they're actually great in electronics because they conduct without getting hot. I mean, you don't want your computer to blow up. When you combine metalloids with a metal or a nonmetal, they usually will take on those characteristics. Well, what's a look at the periodic table without looking at some of the common columns or families? Remember, columns go up and down. We also call them groups or families. Let's take a look at the alkali metals. Now we're considering column 1 without hydrogen. Hydrogen, even though it sits over there, is not an alkali metal. It's not a metal. I've even seen a periodic table that doesn't even put hydrogen in a column. It puts it somewhere between columns 1 and 18. Kind of weird. But alkali metals are soft metallic solids. They are silvery with a metallic luster. They're great conductors, low densities, low melting points. They're extremely reactive. They have to be kept under oil. As you go down the column, the radius gets bigger. Ionization energy is going to go down. It's easier to remove an electron. These are very reactive elements. All they want to do is get rid of that one electron, and so it's a very, very, very reactive situation. They only exist in nature as a compound because they're so reactive. Hydrogen, FYI, sometimes gains an electron to become a -1. So just know that sometimes hydrogen's a -1. And this is when it forms hydrides with other alkali metals like lithium hydride or sodium hydride, so on and so forth. You do need to know that alkali metals react vigorously with water to make hydrogen gas and a metal hydroxide. Here's a couple of videos. One that just shows you how reactive they get as you go down the column, reactions with water. And just kind of a fun one, 1947, we used sodium in World War II. Then we had all the sodium they needed to do something with, and they just started dumping it into a lake in Washington State, and it's kind of cool to see the explosions. Just remember, too, that the alkali metals have unique flame colors. Lithium is that really pretty red, sodium's more of an orange, and potassium is more of a beautiful lavender color. Column 2 are the alkaline earth metals. These are solids at room temp, typically metallic properties, harder and denser than column 1. They melt at higher temperatures. They're not as reactive because they now have 2 electrons they need to get rid of. And the reactivity increases as you go down a column. Again, the radius gets bigger, the electrons are farther away, they're held less tightly, easier to remove the electrons. And here are the flame colors for these elements in case you're interested. I want to go ahead and go back to hydrogen for just a minute, and let's talk about how unique hydrogen is. It's actually quite interesting. We had to do a little deep dive on this during one of my graduate classes in chemistry. Although it is in column 1, it's not an alkali metal, it's a nonmetal. Its ionization energy is double that of the alkali metals. And if you think about it, what is hydrogen? It's a proton and 1 electron. That's it. So When you remove that electron, all that's left is a proton. The nonmetal occurs as a diatomic molecule naturally, H2 gas. It is going to hold on to its electron way more tightly than any of the alkali metals. It does like to react with other nonmetals to form molecular compounds. Think about H2O, HF, and so on. So it likes to share its electrons rather than give them up. Here are some of the famous compounds: hydrogens in water, ammonia, methane. Very, very important in organic chemistry, where C's and H's form bonds and are the backbones for so many molecules. Because hydrogen bonds with nonmetals, in water they break down to form acids or H+ ions. Let's skip on over to the oxygen column. Oxygen, sulfur, and selenium are nonmetals. Tellurium is a metalloid, and then polonium is radioactive, quite rare, but it's a metal. So as you go down this column, you go through nonmetals, metalloids, and metals. So really you get some weird properties going on. Oxygen, either O2 or O3 oxygen or ozone, are gas. The rest are solids. The different allotropes, allotrope is just a different form of the same element, different physical and chemical properties, are oxygen and ozone. Oxygen is also kind of weird. I mean, normally it has a -2 charge, but O2 to the 2 negative ion is what we call a peroxide. And if you look at H2O2, its oxidation number is actually a -1. And then there is something called the superoxide ion, which is O2 with a -1 charge. So there's some weird things happening with oxygen. Sulfur also has allotropes. One of the most well-known is S8, and it is a yellow solid. I don't expect you to memorize S8. If that's going to be in an equation, I would give you that formula. Column 17 and the halogens. Typically, these are nonmetals. Melting and boiling points increase with increasing atomic number. Fluorine and chlorine are gases. Bromine's a liquid. Iodine's a solid. They're all diatomic. F2, so on and so forth. They have highly negative electron affinities. They tend to gain electrons from other elements. The reactivity does decrease as you go down this column, and that's because the atoms get bigger and bigger. A little bit harder to attract the electrons to the nucleus as that nucleus gets shielded from the inner electrons. Fluorine will react with almost anything. It's highly exothermic. The halogens do react with metals to make ionic halides, something you need to know. And halogens react with hydrogen to form gaseous hydrogen halides, which are soluble in water, and they make acids. So you might want to stop and write out a few formulas and prove that as well. And don't forget your strong acids and your weak acids. Hydrochloric acid, hydrobromic acid, and hydroiodic acid are strong. Hydrofluoric is weak, and that's because HF is a very, very, very small molecule. Hydrogen and fluorine hold on to each other quite tightly, don't like to break down very much. I know this has been long, but thanks for hanging in there with me, you guys. This unit is a little bit mathematical, but so conceptual. And you really, really need to understand the reasoning behind things. It's going to be on the test. I'm going to ask you to explain the trends, or why do we see this and this? Why? So I thought longer videos, yeah, a little tedious, but if it helps you to understand those relationships a little bit better, it's all worth it. So the last slide is about the noble gases. These are nonmetals. They're all gases at room temperature. They're monoatomic, so the formulas are simply He, Ne, Ar, and so on. They have completely filled s and p orbitals. Very large ionization energies. I mean, they're stable. They don't want to get rid of their electrons. They don't want to take electrons on. We used to always teach students these are unreactive. They don't react at all. That's not exactly true. We used to call them inert, incapable of forming chemical compounds, but they actually do a little bit. And you'll see those in the next unit. Not a whole lot. Typically, they react with something like fluorine, something that's very electronegative. And I don't expect you to memorize them, but we'll look at those more in the next unit. So now, you're going to do a few assignments that will help you go over and over and over again the different ionic or different periodic trends we see in atomic radius, ionic radius, electron affinity, ionization energy. And over and over and over again, you're going to have to explain why that's the trend. I'm telling you right now, on your test, you're going to see questions like this, probably essay questions, where you need to be able to explain to me why. and it needs to be thorough and in depth. This is a college level course. So I'm looking for positive negative attraction, how far away the electrons are, the effective nuclear charge, how strong that nucleus is. So make sure you really think about learning as you go through these homework assignments. It's not a matter that you get these assignments done and turned in. It's about learning and truly understanding. See you later.